Okay, now what I wanted to do. I want to build these backend and DevOps muscles. As you know, I'm a front-end developer. Mostly, I work. I technically I'm a full stack developer, but mostly I work in front-end. I want to talk about Linux, and I want to first of all see what Linux is as a whole, because before we were type our first command or open our first config file, we need to understand basically in a big picture what it is, the way how hardware works, the way how what kernel is, what is user space, how applications fit in all of this. And the good thing is Linux is modular. Each layer is built on top of another, and it's an amazing way because we can understand these connections and relationships. And we can basically not only use Linux, we can engineer with Linux, we can be comfortable with Linux. In this one, we are gonna, first of all, I hope you like I changed my wallpaper. Hope you like it. We need to answer some big questions. What exactly is the kernel? What does it do? How do system processes fit into the big picture? What are shells, libraries, daemons? Where do they live in the system hierarchy? And all of the other things. Basically, where are you? This is about Linux as a living organism. This is about the skeleton that we need to learn, this video at least, in order to do anything else. Now, let's start. Linux, like this, and I'm gonna center it here. Maybe increase it a bit more because I don't think I'm gonna do anything else, so I can keep it in the middle of the screen. All right. This should be right. So let's talk about Linux and let's talk about the big picture. Now, Linux is an extremely complex machine. Any operating system is extremely complex, but Linux especially has a lot of pieces that run together, that work together. And now, okay, this is the big picture. Now, what is the big picture? Linux in itself, any operating system, it's very complicated. There's a lot of moving parts there. And we need to, instead of learning every nook and every cranny, we need to simplify it a bit, create a mental model that is a bit easier to understand. And we can do this through abstraction. We can ignore most of the details that make a piece that we want to understand. And we need to focus on what the basic purpose of it is. For example, when you use your phone, you don't usually think, and you don't need to think about how the camera works and how the chips communicate. And when you drive a car, you don't need to know how the gear shift works and how the gas combusts into energy. You just need to drive the car and you just need to use the phone. You just need to know how to use the phone. Another possible abstraction could be you watching your football team, and there is a lot of tactics involved into it, a lot of plays, a lot of different movements. And yet, for us, more or less, the most important thing is how many goals our favorite team has scored. And with our basic level of abstraction, we can basically understand the simplest and the most common problems and issues. If your local football team is losing by a huge margin, let's say 5 or 6-0 to a club from the first league, you can basically abstract that one of the reasons your club is losing by this much is apart from tactics, is that the players are not good because the club doesn't have enough money. So you can actually narrow the problems down to a couple different points that you can use, and you can maybe even go a little bit deeper to see why the players are not as good, why your club is not earning money, and things like that. Now, we will now provide a high-level overview of different subsystems and elements that make up the Linux system. A lot of the details will be ignored because in the end, as the title says, we just want to talk about the big picture. Our Linux system has 3 main levels, and these levels are as following. Hardware, which is the memory, the central processing units which perform calculations, all the other components, disks, network interfaces, anything that is one of the ways my professors have explained it to me, that anything you can touch that consists, that is part of a machine, is the hardware. Then we have kernel, and this is the core of the operating system. It's the software that tells the CPU what to do and where to look for the next task. And it manages the hardware, it manages main memory, and it's the connector, it's the mediator, it's the main interface between the hardware and any running program or software. And the next thing is the process or the processes, which are the programs that the kernel manages. And they make the system upper level called user space. Now, I'm just gonna draw this. I'm gonna use a different color. Wait. I think I have, this works. This is great. It's a bit fat, but I'm not gonna complain. So first of all, what do we have? We have, is this even the same color? I hope it is. So we have the hardware, which consists of the CPU, of RAM, disks, and let's say network ports. The next thing is the kernel, and the last thing are the user processes. So the kernel consists of system calls, of process management, memory management, and let's say device drivers. And what we have in the user process, we have GUIs, we have servers, and we have the shell. There's one core idea in Linux, and this core idea consists of kernel mode versus user mode. To simplify this, the kernel is the god. The kernel mode is the god mode. Kernel has the full access to the CPU plus memory. It's super powerful, but at the same time super dangerous. If something messes up, the entire system is compromised, the entire system could crash. Now the user mode is the playpen mode, because the process only gets safe parts of memory and CPU. If they crash, the kernel can clean it up and the rest of the system survives. So the kernel space and the user space is the memory that the kernel owns and the memory that the user program owns. But that's the problem in the kernel mode. Yeah, you can touch anything, CPU, memory, devices, but if you screw up, boom, the entire system face plants. So Linux is smart enough to say, here, I'm giving you the environment and you can play around, but don't burn down the whole house. Unless you run as a root. That it's like giving the kid scissors or the chainsaw. Here I wrote RAM, or we can call it main memory. Everything lives here inside RAM or main memory as zeros and ones, as bits. Then we have the CPU, which is the machine that reads instructions and data from memory. It does the work and then writes results back. Now, another term that we might often hear in reference to memory is the state. So if the RAM consists of, can I just draw the lines like this? Yeah. I'm still learning. Okay, so if the RAM consists of a combination of zeros and ones, a state is this particular arrangement of bits that we save. If we have this particular arrangement, this is one state. Another state would start with a 1, have a 0 there, and it can have the rest the same, but it's still a different state. And when it comes to referring to different states, instead of, you know, the number of bits can go up to millions of bits in memory, it's often easier to use more abstract terms like waiting for input or loading or building up the application. Okay, now let's go to the kernel. The kernel is highly dependent on the main memory. Wait, let me maybe use a different color here too. So the kernel, like this, is highly dependent on the main memory. What kernel does, it takes the memory and, for example, it splits it into subdivision, and it must maintain state information about these subdivisions. Like let's have the same memory state. So we can split it like this in two parts, and it must maintain state information about these subdivisions. What the kernel also does, it's in charge of managing tasks in some other areas, like processes. Because the kernel is in charge for determining which processes are allowed to go to the CPU. Kernel also manages memory. The kernel needs to keep track of all memory. What is currently allocated, what might be shared between processes, what is free. Kernel also handles device drivers, because it's the kernel job to operate the hardware. Of course, system call, the kernel calls the system calls. So process management is basically how Linux keeps all the programs of our computer running without stepping on each other's toes. So what a process is nothing more than a program that's currently running. What a program currently runs can be the browser, the music player, the spreadsheet. The kernel is managing when they start, when they pause, when they stop, and most importantly, who gets to use the CPU. Now, I don't know how used they are, but they are single core CPUs. And on single core CPUs, there can be only one process. Because only one process can use the CPU at a time. But since we want to do more things, Linux fakes it, in a sense. So it gives a certain amount of time, called a time slice, to each process, and then it switches to the next one. So the switching happens so fast that for us it feels like everything is happening at the same time, and that's called multitasking. We can also switch from one process to another, and it's called the context switch. So the CPU, when it comes to context switching, I'm also gonna say the CPU interrupts the current process and it switches into the kernel mode and it handles back control to the kernel. Then the kernel records the current state of the CPU and memory, and this will be essential to resuming the process that was just interrupted. There might be some work here that could be done during the time slice, like collecting data from input or output or some other operation. Now the kernel is ready to have another process run. The kernel looks through the list of processes and chooses one. And then the kernel prepares the memory for this new process and then prepares the CPU as well. And the kernel tells the CPU how long the time slice for this new process will last. And then the kernel switches the CPU into user mode and has control of the CPU to the process. So what happens is that the kernel sneaks in its own work between these tiny slices of time. That's why we say the kernel run between processes. On modern machines with multiple CPUs, things are a bit smoother because processes can actually run at the same time. But the kernel often uses the same logic to make sure everything stays balanced and no single process hogs the system. Oh, right. I had some technical difficulties, so I had to restart my tablet. Hopefully now, let me just turn it on. It's my wallpaper. And we will continue now with talking about the Linux big picture. Now, as we said, the process management, it deals with everything relating to processes itself. Starting, managing, terminating, scheduling, restarting, resuming, and all of the other concepts related to processes. For example, let's say we have a web browser, and what else could we have? GIMP open at the same time on our computer. Yeah, let's leave it like this. Let's leave it like this. So this is supposed to be like this, and this is supposed to be like this, and the third one is supposed to be like this. Yeah, now it looks a bit better. The GIMP looks something. I hope I will draw it now naturally. I know he has a brush here and his eyes are a bit, yeah. So let's say we have our browser, Chrome, and GIMP running at the same time. Now, we might notice that we have them open at the same time, and if we put them divided on our window in the same place, they typically don't run at the same time. And as I said, it's because on one core CPUs, processors are fighting for processing power, and each process is using the CPU for a small fraction of a second, then another one for another small fraction of a second, and all the way. till the end. And as I said, this is called context switching. Now, let's talk about, should I write it here? Let me just move this here, maybe reduce the size a bit. Yeah. Now, let's talk about memory management. Now, when it comes to memory management, the kernel needs also to manage memory during a context switch. That can be a pretty complex job because what the kernel needs to do is kernel can't allow user processes access to its own memory. First of all, each user process needs its own section of memory. One user process can access private memory of another user process. User processes can share memory. Some memory user processes can be read-only. And the system can use more memory than is physically present by using disk space as auxiliary. So here what I'm gonna write is kernel manages memory during the context switch. What else do we have? Device drivers. What is interesting about device drivers? What can kernel do with the devices? Devices are pretty easy explained because a device can only be accessed in kernel mode. Because user processes improperly accessing devices, such as requesting a computer for a shutdown, could break the machine. So that's also pretty interesting. Okay, now what are system calls? We know that user programs can do everything by themselves. So as a matter of fact, a lot of things are forbidden for the user programs. So if a program wants to talk to the hardware or to the devices, it has to ask kernel for help. And there are two syscalls that are especially important for starting processes, fork and exec. We have fork and exec. Fork makes a copy of the current process. And exec is how you actually start a new program. It replaces the current process image with the one that we asked for. So how does this work in real life? When we type ls in our terminal, the shell doesn't magically know how to list files. Instead, the shell itself calls fork to make a copy of itself. And then that copy immediately calls exec ls, which transforms the copy into the ls program. So what's running our command is actually, we have a child process, which was born from the shell and then swapped out to become the program we wanted. That's why on Linux, pretty much every process we run can be traced back, can find its ancestry back to one parent process, the very first one called in it. There's something biblical, something religious in this, almost. And I think we have one more thing to mention, and that is user space. I'll move this down a bit. Now, as you already know, kernel has and keeps its own special memory area, and we call this the kernel space. And everything else, including the memory that belongs to the programs we actually run, is called user space, or informally userland. The user space Let's say the user space is all the memory apart from the kernel memory. And the user space is similar to a busy city on the top of the stable foundation that the kernel provides. And each process in the user space is a state in memory. But together they form the environment where the action happens. And even though from the kernel's point of view, all processes should be equal, in practice, they can play different roles. We can imagine them arranged in layers. At the bottom layer, we have those simple small services like caching or logging, things that do one job. Then we have utility services in the middle layer, bigger systems like mail, printing, or databases. And at the top layer, we have the applications that the users interact with directly, like browsers, user interfaces, and editors. But user space is more or less free for all. Programs depend on each other, and it's not clear where they fit. You know, a web server could be considered a top-level application because it handles complex tasks, but it can also be a middle-level service. It's, you know, other programs rely on it. Now, what is the shell? The shell is our gateway into Unix. It's the program that takes the commands we type into a terminal. It figures out what they mean and runs them. And sometimes these commands are full programs, sometimes they're just built-in tricks of the shell itself. Shell can also be, so let me write here, Unix commands. But we can also use the shell as a complete programming environment. Programming environment. Now, the standard shell historically is called the Bourne shell. It's located in the following directory. It was created back in the Bell Labs days of Unix. And every Unix-like system still needs some form of Bourne shell to function. Now, Linux, and now we're going to talk about Linux, uses an upgraded version called Bash. Bash is another interesting shortcut for Bourne again shell. That's the default shell we'll find of most systems today. And when we see bin shell on Linux machine, it's usually just a link pointing back to the bash. A good thing about the shell is that mistakes are cheap. If we type something wrong, like instead of SL, I can type LS, I can type SL, and we have typed something wrong, the shell just shows us the error. You can do it again correctly, and there won't be any permanent harm done, which is an amazing thing in order for experimentation. Now, so initially when we install Linux, we don't run everything as a super powerful root user because that's dangerous. Instead, we create a regular user account, and it's going to become our day-to-day login. Once we have been logged in, the way we interact with the system is usually through a shell window, which is a terminal, which is this thing that you see in the bottom right corner of my tablet screen. we open the terminal and boom, we have the shell running inside that window. So if we see here, if we see here, this is a prompt. And on Ubuntu, it looks something like this. So it's the name. And then I have host. And then I have path. And then I have the $sign, which means our username. Which means our username, the name of our machine, and the folder or path where we are currently in. It usually ends with the $sign. Now, one command we can try is cat. And it stops here because in order for cat to work, we need a file. And cat will print the contents of a file. So if I go, I need to find a good environment. So projects, auto cutter. So this is a project of mine that I've been working on. And if I type cat readme.md, here I will see the contents of a file that I have on my machine. This is one of the simplest tools. There's also the clear function, but this is one of the simplest tools in Linux. It shows us what is inside the files, and it's a building block for a lot of things we will learn in the future. All right, let's go back to the theory. Every process in Linux needs a way to get data in and send data out. That's where streams come in. A stream is a pipe that carries data from one place to another. And by default, every program gets two streams automatically. You have the standard input and the standard output. So the standard input and the standard output are the streams that are by default automatically there. Standard input, or stdin, is where the program reads from, and the standard output is std out, is where the program writes to. If you remember, we went here and I typed cat without any argument. Nothing happens because cat is waiting for an input. If I type something like fff, if I press enter, the same line is printed back to us. What is happening is that cat is reading from the standard input. Our standard input in this case is our keyboard through the terminal, and it's writing to the standard output, the same terminal window. When I'm done, I press Ctrl D on an empty line. That's gonna send an end of file signal. It's gonna tell cat there is no more input. There's a difference between Control D, which is not the same as Control C. Control C is forcefully killing the program. You notice something. You notice that the terminal is hooked as both standard input and standard output in this case. That's why what we type shows up again in the same window. We are not limited to the keyboard. We are not limited to the terminal output or to the screen. The input stream could come from a file or a device or as an output of another program. And the output could go to a file or our screen or be piped into another program. There's also another stream. I won't mention it again. We will talk about it later. Now there are some other basic commands. I don't know if I will go over the commands, but for example, we have Let's do this quickly. Let's do this quickly. We have ls. ls lists the contents of a directory. And this is the default view, but we can have many useful options like ls l. This is a detailed or long listing. ls f is gonna display the file type information. I mean, it's really cool, but I don't think we need this right now. We have cp, which is copy. So I can copy readme.md to readme to md. If I type ls, I'm gonna see my readme2 file here. Move actually moves files or renames them. If I say readme2 and if I say test here, it will actually rename my readme2 file into test. If I type ls again, it's test now. What else? We have touch. Touch will create a file. Empty. If I do ls, now I have empty and test, which I don't need, which is a great thing because I can do rm. rm deletes or removes a file. If I type in test rm empty, I can remove both of these guys. What else? Echo. Hello. Echo is just printing the argument to the standard output. If you remember, I can navigate directories. If I type cd is change directory. It's a command to change a current working directory. Make directory. This is going to create a new directory. I don't want to do any of this now, but because these are quite simple and with use everyone can learn them. But there's an interesting thing here. Now, shell can also do something that's called globbing or wildcards, which is how shell. Let me also write this here. This is how the shell can match multiple files with just a pattern instead of typing every file name out. For example, if I say here, let me clear this. If I say echo and the star, which is the most common wildcard, it means match any number of characters. This is gonna list everything in the current directory, but I can do this as well. I can echo something, and what happens here? The echo is gonna match everything that has a wildcard at the beginning and it ends in end. If I press enter, it's only gonna match backend and frontend. If I do echo read and then a star, it's only gonna match readme because it starts with everything with read. Everything else is dynamic. It's a wildcard. For example, I can do touch readme 4 md, and if I do again echo read, it's gonna read both of these. Let me remove readme 4. I don't need this here. What else? Oh, there's the question mark. The question mark matches exactly one character. So if I do echo 1, 2, 3, 4, and it's only gonna match backend, but if I do another question mark, it has 5 letters now. It's gonna match frontend instead of backend. Okay, now once we can grab file names, we need to find content inside files. This is where grep comes in. So globbing and wildcards, I'm just gonna say we have the star, which is the most common wildcard, and let's say and the question mark. These are only 2. We can have more wildcard, but let's mention 2 only for now. Now, how to find content instead of how to find content inside of files. Let me go back here and let me just do cat readme. Okay, I just want to see what do I have here. Okay, let's clear this and let's, for example, do grep user readme-md, and this will show all the lines in that file that we have that contain the word user. And I remember seeing only allows the user to adjust the threshold, so I said, okay, let me just use user. If there are more, let me maybe find readme-md file. Let's search for file. Grep file readme-md. Pied up for auto. So okay, I mistyped this, misspelled it. Frontend sends the file to the backend. Backend converts the file to WAV. These are the two lines where files found. But you know what's interesting? I could also search not only in one file, I can search in the whole directory. Let's say file backend. So what will happen now is we will search for every instance of file in the backend directory. Oops, I forgot to put a wildcard here. And look at this. These are all the instances of file we have inside every file in our backend directory. What else? Let me just do this again. Cat readme-md. Let me. So if I do, where have I found it? User. We only see one instance of user, but I also see here that I have a user only with an uppercase U. So I can do grep user readme with this option here. We can set our search to be case sensitive. And also there's also regular expressions. There are whole signs, so on their own, let's do them later. What else do we have? What are some other commands? I can use less readme.md. If I run something like less readme-md, we are gonna see the file one screen at a time. If I press spacebar, I can go to the next page, so to say. If I press B, I'm going back. If I press Q, I can quit. Yeah, there's a fun fact. Less is actually an improved version of an older program called more. That's why there's this old joke saying less is more. Less actually isn't just for files. We can also send the output of another program into it, like for grep. For example, wait, look at this. Grep IE. Let's search for this in the whole backend. But if I pipe it to less, so there's no what? Okay, maybe not. Let's maybe. All right. We have a lot of cases here, and if I press space, I can go through them. Let me close this. What else do we have? We have pwd. It prints the working directory. It shows us which folder we are in right now. Okay. There are a lot of other commands like diff. Diff is used to see the difference between text files. I can use file. File is used to see the format. File is actually quite good. Unicode text, UTF-8 text. Yeah, there's a lot of things. Ooh, there's actually something. Can I do LSLA? Now look at this. If we type only ls, we actually see only these three files, these two directories and this one file. But with LSLA, we see what we call dot files and dot directories. These are the files and directories whose name begin with a dot, obviously. And so we don't, some programs don't show them by default. So we won't see a complete mess when we list the contents of a home directory. What else do we have? We have the shell variables. There's the command path, all the other things. Okay, as I said, now let's talk about something that's a bit more complex. By default, as we said, a command writes its output to the terminal. But using this simple command, we can send that output into a file instead. So we can do something like this. Let's see if this will work. LSLA. I'm gonna do this. This is the command, and I'm gonna create a new file. Now I'm gonna type the name of the file, listing. If listing doesn't exist, let me move it. Let's move this here. So if listing doesn't exist, it will be created. If I now type in the contents of this directory, we have a listing, and I can do cut listing, and I see the same output I would get if I would type LSLA. Now, if we run this again, nothing happens, it will be overwritten, but if I don't want to overwrite it, I can add another one of these less than signs. Now listing is just concatenating the content on top of each other. Then we can also use the pipe symbol. This is the pipe symbol. For example, I can do LSLA, and I can then search for anything that matches end at the end. What? Front end is a directory. Oh, I made a mistake. Now what I did here is I mixed globbing with grep's pattern matching. Because when I run this, the end part, this part, is being expanded by the shell, not grep. So before even grep runs, the shell looks in our current directory for files that end with end. If there are matches, it replaces end with these file names. If there are no matches, it literally leaves end there, and grep treats it as a file name, not a pattern. So what I should do is LSLA grep end. Oops. So we want grep itself to look for lines ending in end. This symbol means end of line. Let me clear this. Oops. Now look at this head. Let's see. What head does, it just prints out the first 2, 3, 4, 5, 6, 7, 8, 9, 10 lines of a line, if it's of a file, if it's more complex or longer than that. And if I do this now, and if I add a pipe, what happens here is that head is grabbing the first lines of the CPU file, and then tr is translates all lowercase letters into uppercase. And with pipes, we can chain commands together, like, you know, Lego blocks, and we can build powerful commands. Let me clear this. Now, there's something else. Even if we redirect output, we'll still see some error messages on the terminal. And this happens because Linux has a second stream called standard error, or std err. Programs use it for warnings and errors. Okay, now let's say we want to list a directory that doesn't exist. And now if I do this, basically saying this is the symbol for a direction, and this symbol means take the standard output of the command and put it into this file, which means that the standard output will be redirected into a file called f. If f doesn't exist, it will be created. If f already exists, it will be overwritten, emptied, and then written. What actually happens is that ls fails because this folder directory doesn't exist. There's no normal output, which means that f, which doesn't exist, actually it does. Look at this. If I try to see the contents of f, it's empty. There's no normal output, but we still have the error message here appearing in the terminal because the errors go to standard error, not standard output. And we only redirect standard output with this redirect command. If we want to catch the error as well, let me remove f, let me remove listing. We need to redirect the standard error as well. How can we redirect errors? We can use the following command. Let me move this up. And here, I can say, okay, send the normal outputs into F and send errors into E. And if I type ls now, we have F and E. F will be empty, but E will contain the error that we actually saw in the window just now. We can merge these commands together. I can say, let me move this up, doesn't exist. And I can say F and this, if I see the contents of F. This means send standard output to F and send the standard error to the same place as the standard output. We can also do the inverse. We can redirect the input redirection with this command. So we had these less than, we can also do greater than, which is the inverse. Basically meaning that programs can read input from the keyboard, but we can feed them a file instead, like oops, head pros CPU info. What else? Let's see about the processes. How to see a running processes. Okay. So how can we see our running processes? We can type in and we can use the command ps. And if I do now here, psx, you can actually see all the processes I'm running. I can also use psux, which will show more details. psw, it shows full command names, not just what fits on one line. We can combine them. We can, for example, type psaux or stuff like that. Now, let's do psx. And this right here, this first column, if I scroll all the way to the top, you will see that it's named PID, which is the process ID. And we could actually do kill. I won't do this because I don't want to break my computer, but I can do 38668. This is the bash. If I run this command now, I would terminate bash. I would kill it. Basically by sending a signal. It's a message to a process from the kernel with the kill command. That's all I need to do. Okay, there are also background commands. Oops, I'm not interested in that. Oh, this is actually interesting. Let's run lsla again. So every Unix file has a set of permissions that determine whether we can read, write, or run the file. So by running this command, we actually see the permissions. These are these weird combinations of D, R, W, and X right here. It's also called the mode. It represents the file's permissions and some extra information. We have four parts to the mode. The first one is this D, a dash. So what? If you select all the listings that have D in front of them, you will notice that these are directories, and the rest of them are files, which means that the first character is the file type. A dash denotes a regular file, meaning that there's nothing special about it. The D denotes the directory. Now, the rest of these guys denote and contain the permissions. So we have the user permissions, group permissions, okay, and the other permissions, and they're always ordered in that order. For example, I have this in this file right here. I have rv dash. What does this mean? Let's talk about what this means, but this is the user permission. The second group of three is the group permission, and the last one is other permissions. R means that the file is readable. W means that the file is writable, and X means that the file is executable, meaning that we can run it as a program. A dash means nothing. The permission for that slot in the set has not been granted. So the first part, the user permissions, that pertains to the user who owns the file. So we have the permission to read, we have the permission to write, we don't have the permission to execute. Interesting. Our group has the permission to read and write, doesn't have the permission to execute, and the others only have the permissions to read. We can also modify our permissions, and we can change it on a file or directory by using the chmod. We can pick the set of permissions that we want to change, and then we can change it. I don't want to go too deep into this right now. There are actually commands, for example, chmod like 644, and I can do readme. And if I do this again, you can see that permissions have changed, meaning that the user can still read and write, but the group and the others can only read. This command is called an absolute change because it sets all permission bits at once. What else can be interesting? I skipped a lot of things here. We can also run the commands as the super user. That's actually also interesting. we can just do sudo. I will have sudo. Sudo can actually run ls, and now it requires me to type in my password in order to run ls. All right, so that's it. In the next episode, we're going to talk about devices. I hope you had fun, and see you in the next episode. Bye bye.